Welcome to this lecture series in complex numbers. In this lecture, we look at a very nice application of the things that we have learned so far. And here is the puzzle or problem that we will solve. So suppose we have three distinct complex numbers, z1, z2, and z3. Then we want to show that these form the vertices of an equilateral triangle if and only if this algebraic condition holds. So the very geometric notion of 3 points being the vertices of an equilateral triangle is captured algebraically. That's very nice. All right, so there are two parts of this. One is that once you assume that these are indeed vertices of an equilateral triangle, then you show this. That's the easy part. We will do the other direction. So suppose indeed that we have this algebraic condition satisfied, then our goal is to show that z1, z2, and z3 are vertices of an equilateral triangle. But we will reduce this to a more palatable situation. So suffices to show, and this is an important note, it suffices to show that there's something wrong. That there is tau, a complex number, such that z1 minus tau, z2 minus tau, and z3 minus tau are, the vertices of an equilateral triangle. So this is a very simple observation. All we are saying is that if 3 points are vertices of an equilateral triangle, then so is the translation of those 3 points by a common vector. So it's not just suffices to show, it is equivalent to show. So wanting to show the z1, z2, z3 are vertices of an equilateral triangle is equivalent to showing that these are vertices of an equilateral triangle, because translations do not change the nature of a triangle. Okay, so this is, what we will do is we will find a suitable tau such that it will be easy to show that the corresponding translated points are the vertices of an equilateral triangle. All right, so towards that, here is a very simple claim. So we claim that for any tau complex number, we have z1 minus tau whole square plus z2 minus tau whole square plus z3 minus tau whole square is equal to z1 minus tau z2 minus tau plus z2 minus tau z3 minus tau plus z3 minus tau z1 minus tau. So what we are saying is that this condition, the algebraic condition that we have, remains preserved under translations. All that has happened is that the zi's are replaced by their translated cousins. And of course, this is just a matter of simple computation. So this proof that does not deserve to be done in great detail, but here is the thing. The left-hand side is summation I equals 1 to 3 zi minus tau whole square, which is this summation. The summation notation eases out the computation. So this is just some basic algebra, which is equal to summation I equals 1 to 3 zi square plus 3 tau square minus 2 tau summation I equals 1 to 3 zi. So I'll let you verify that what I've done is correct. So that's the LHS. The RHS is, here the summation notation will not serve us too much, but here there are 3 terms in the RHS. The first term is z1 z2 minus tau z1 plus z2 plus z1 z2, just computation, plus z2 z3. So this is the first term. Now we are computing the second term, plus z2 z3, and then we have the third term, which is z3 z1 minus tau z3 plus z1 plus z3 z1. I think I've done a lot of wrong things here. Sorry, this is completely wrong. This is completely wrong. This is a tau square. This is tau square. This is tau square. This is tau square. Right? I had already multiplied z1 with z2. I just did it 2 times without noticing. So that's what it is. And rearranging the terms, the RHS can be written as z1 z2 plus z2 z3 plus z3 z1 minus 2 tau z1 plus z2 plus z3. I'll explain this thing. So where is this term coming from? We have these three things. If we add them, we get that. And lastly, this is plus 3 tau square. So that of course comes from these 3 tau squares. And clearly the things match because 3 tau square appears, 3 tau square appears here, this term appears here, and this is equal to that. That is our hypothesis on z1, z2, z3. So that's the proof of this claim. There's nothing very interesting going on. So now we will choose our suitable tau. So fix or define tau to be equal to this. So that's our definition of tau, and we will show that z1 minus tau, z2 minus tau, and z3 minus tau are the vertices of an equilateral triangle. I will explain the geometric meaning of this tau, but first let me record what is our goal. Our goal is to show that z1 minus tau, z2 minus tau, and z3 minus tau are the vertices of an equilateral triangle. Geometrically, what's happening is we have z1, z2, and z3. Tau is the centroid of this triangle. Let me make a bigger thing. So tau is just the centroid. This is a very general thing. If you have 3 points z1, z2, z3, then this tau is the centroid of the triangle formed by these 3 points. So what we are doing is, basically when we are considering these 3 points, we are making the centroid as the origin of our complex plane. You can think of it that way. And that makes life much easier, as you will see. The algebraic reason of doing this is the following. So here we have two things that we will note. As we have already proved, we have this. Okay, so let us define. It'll be a good idea to introduce this notation. Define W1 as Z1 minus tau, W2 as Z2 minus tau, and W3 as Z3 minus tau. And note that, this is an important note, that we have W1 square plus W2 square plus W3 square is equal to W1 W2 plus W2 W3 plus W3 W1. So this is what we proved in the previous claim, in the previous page here. So we have that, but we have further that W1 plus W2 plus W3 is 0. That you can just immediately verify by substituting the value of tau here. And this is why this was chosen for the, this is the algebraic reason for choosing this. We have this extra equation which will help us immensely. So we have that. And our goal is to show that W1, W2, and W3 are the vertices of an equilateral triangle. Before we get there, we'll make one further adjustment or modification, or you could call it a piece of trickery, and that is the following. Define P1 as, well, something, it's this, but we will divide by, we'll also scale by the magnitude of W1 square. Now this is equal to 1. What I've just written is equal to 1. But before I do this, this is what I want to do. But before I do this, I need to justify that this guy is non-zero. So first we will justify that. So now we have another claim. So our claim is that W1 is non-zero, W2 is non-zero, and W3 is non-zero. So here is the proof. Again, you can try this for yourself, but suppose for the sake of a contradiction that suppose W1 is 0. Then from the first of these two yellow things, what we get is W2 square plus W3 square is W2, W3, because two terms on the right hand side go away. And this implies W2 plus W3 whole square, which is equal to, so I mean, this becomes equal to 3 W2, W3. Because if you just expand out this guy, you get W2 square plus W3 square plus twice of that guy. So that's equal to thrice of W2, W3. But what is W2 plus W3? Because W1 is assumed to be 0, W2 plus W3 also becomes 0. And hence, what we get is 0 equals 3W2 W3, which implies W2 is 0 or W3 is 0. But now, if suppose this were 0, then using this equation, since two terms here are 0, the third would also be 0. So the implication is really that W2 is equal to 0 and W3 is equal to 0. I don't know why I used this horrible color suddenly. So we have this conclusion that if one of these Wi's are 0, then the other two are also 0. And what that means is that if one of these Wi's are 0, all the Zi's are equal. Because if all the Wi's are 0, then all the Zi's are equal to tau, which contradicts our hypothesis that Z1, Z2, Z3 are distinct complex numbers. They are three distinct complex numbers. So that is the reason why none of these Wi's are 0. All right, so that's some side claim. And now here is our final adjustment or reduction. Define P1 as W1 bar divided by mod W1 square, which is of course equal to 1. That's not surprising, but I will write it that way because that is meaningful to write. So this is equal to 1. And now what is P2? P2 is W2 W1 bar divided by mod W1 square. I will explain the geometric meaning of this modification. W1 bar by mod W1 square. So if you ignore the scaling factor for the moment, what is happening is P1 is the P1 is obtained by rotating W1 counterclockwise by the angle that W1 makes from the x-axis. W2 is also obtained by rotating with the same amount, and W3 the same amount. So this was W1, that was W2, that was W3, let's say. What we are doing is we are kind of rotating, and this becomes the new W1, which is P1. That becomes the new W2, which is P2, and this becomes the new W3, which is P3. So all we are doing is rotating this. But in the process, since we are multiplying by something that does not necessarily have magnitude 1, we may have scaled things. So it is just best to scale things so that one of the things has magnitude 1. That's the most convenient, and that is why we have chosen the scaling factor as the magnitude of W1 square. So I hope that made sense. And again, we note that P1 square plus P2 square plus P3 square equals P1 P2 plus P2 P3 plus P3 P1, and P1 plus P2 plus P3 is 0. So this is immediate from the yellow things here. Just substitute the expression for P1, P2, and P3, and you will see that these denominators cancel out, and the scaling factor, which is common, also cancels out. And what we really need is the following. The third one, I'm sure you see why the third one holds. So why does the third one hold? This is just an immediate consequence of the first two. So to justify this third one, the reason for the third one is the following. We have P1 plus P2 plus P3 whole square equals P1 square plus P2 square plus P3 square plus twice of P1 P2 plus P2 P3 plus P3 P1. Maybe that is not even visible. That's what it is. But now we use the first yellow thing, so the right hand side becomes that guy. And using the second yellow thing, the left hand side becomes 0. And therefore we have the third yellow thing. And what we will use is just the second and the third. Basically, I mean, these two conditions are equivalent to those two conditions. So, but this is the form that we will really need. So now finally, here is the last step. Consider the polynomial z minus p1, z minus p2, z minus p3. Z is some variable complex number, you can think of it that way. So consider this expression, and what is this? If you just expand it out, as we have discussed in our previous lecture about polynomials and roots, this is z cube minus p1 plus p2 plus p3, z square plus p1 p2 plus p2 p3 plus p3 p1 z minus p1 p2 p3. That's what this is. But as we've seen, this term is 0 and that term is 0, so the thing is just z cube minus p1 p2 p3. Okay, and what that means is that this expression is same as that expression for each complex number z, in particular for z equals p1. So what happens if we substitute z equals p1 here? We get what color should I use? Let me use pink. So if we substitute z equals p1 on the left hand side, we get 0, right? Because if you substitute z equals p1 here, we get p1 minus p1, and hence that is 0, and that should be equal to this guy. So therefore what we get is 0 equals p1 cube minus p1 p2 p3, but p1 is equal to 1, right? P1 is equal to 1, so that means 1 equals p1 p2 p3. So that's what we reduce, and hence if we just take a note of this, using this equation, what we can write is z minus p1, z minus p2, z minus p3 equals z cube minus 1. We have this. And since p1, p2, p3 are pairwise distinct, why? Because w1, w2, w3 are pairwise distinct, because z1, z2, z3 are pairwise distinct. So since p1, p2 and p3, I mean, we do not really need to make that comment actually. So this I mean, the implication is thus p1, p2 and p3 are the 3 cube roots of unity, because this equation shows that p1, p2, p3 are precisely the roots of this polynomial z cube minus 1, and hence they are precisely the 3 cube roots of unity. And the 3 cube roots of unity look like this. This p1 is of course 1, as we have already seen. This is p1. This diagram is not faithful to geometry, but I hope you see. I mean, basically what I'm trying to say is that this is the unit circle. This is 120 degrees and this is 240 degrees. This is omega square. So one of this is p2 and the other is p3. So indeed p1, p2, p3 form the vertices of an equilateral triangle, because they are the 3 cube roots of unity, and the 3 cube roots of unity form the vertices of an equilateral triangle. So our goal was to show that our goal was to show that w1, w2, w3 are the vertices of an equilateral triangle, but that was equivalent to showing p1, p2, p3 are the vertices of an equilateral triangle, because once you do it for p1, p2 and p3, all you need to do is scale p1 by this guy, p2 by the same guy, p3 by the same guy, and then rotate. Or you can just think of this operation as a rotation and a scaling. So w1, w2, w3 are obtained by rotating and scaling p1, p2, p3, and hence the equilaterality is preserved in that process, and therefore we are done. So writing all that is not going to help, and hence I skip that writing, and I hope you follow everything. So this is a very nice proof of this fact that this algebraic condition implies a geometric condition, and conversely. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.